We're going to walk through some examples where we are going to find the critical number of a given function. I've written down a method that we can follow just to make things easier. The first function that we're going to find the critical numbers for is the function f of x is x cubed plus x squared minus x. Our first step is to calculate f prime at x. So let's do that. F prime at x is equal to 3x squared plus 2x minus 1. And then our second step is we're going to set that equal to 0. We can factor this. This is 3x minus 1 and x plus 1. That's equal to 0. And then if we set both of these factors equal to 0, we get that x is equal to 1/3. And we get that x is equal to minus 1. These two numbers then are our critical numbers. Over here on the right, I have graphed this function just so that you can see what it looks like when we have a critical number. When x is -1, the slope of our curve is equal to 0, and we have what's called a local max. And then when x is at 1/3, we also have a slope of 0. And at that point, we have a local min. Let's now look at our second example. In this example, we're given that f of x is equal to x cubed plus x squared plus x. We're going to begin by taking the derivative. F prime at x is equal to 3x squared plus 2x plus 1. And we're going to set this equal to 0. Now we have to factor this. When I look at this, I cannot see an easy way to factor it. So we are going to have to use the quadratic formula. Let me just go ahead and put that over here. The quadratic formula tells us that x is -b plus or minus the square root of b squared minus 4ac, all divided by 2a. Let's see what this gives us. X is equal to -b, so that's -2, plus or minus the square root of b squared, so that's 2 squared, so that's 4, minus 4 times a, which is 3, times c, which is 1, all divided by 2 times a, which is 3. Let's look at this part right here. That is equal to 4 minus 12, which is minus 8, and that is less than 0. So this tells us that we have no real roots. And whenever we have no real roots, we have no critical numbers. Let's now look at the graph of this function so that we can see what a function looks like when you don't have any critical numbers. Notice that our function is always increasing. The slope of the function is never equal to 0, and there are no max or mins, so there are no critical numbers. Let's look at our third example. Our function f of x is equal to the square root of x times 1 minus x. We're going to begin by taking the derivative. F prime of x is equal to, now we have to realize that we have to use the product rule. We have a first function and a second function. So our derivative is the first function, which is the square root of x, times the derivative of the second function, which is -1, plus the second function, 1 minus x, times the derivative of the first function. The derivative of the square root of x is 1 over 2 root x. If you haven't memorized that, that's probably worthwhile memorizing. It just saves time. Now we need to simplify this. Let's get a common denominator of 2 root x. So we're going to multiply this term by 2 root x. So that gives us a minus 2 Root x times root x is x, so we have minus 2x. And then from the other piece, we have a 1 minus x. This gives us 1 minus 3x in the numerator, and then in the denominator, we have 2 root x. We are first going to check where the derivative is equal to 0. So we're going to take the numerator and set it equal to 0. So we have 1 minus 3x is equal to 0, and this gives us x is equal to 1/3. So that is a critical value. Now we're going to see where our derivative is undefined. That is going to happen when our denominator is equal to 0. So we have 2 root x equal to 0, and that happens where x is equal to 0. Now, we can't just assume that this is going to be a critical number. We have to go back up to our original function, and we need to see if it's defined at 0. F at 0 is the square root of 0 times 1 minus 0, which is just 0, and it is defined. So we can then know that x is equal to 0 is also a critical number. I've graphed our function up here on the right. At 0, we have what's called a vertical tangent, and that's why the derivative is not defined at that point. And then at our second critical number, the slope of the tangent line is equal to 0, and we have a local and absolute maximum. Let's now look at our fourth example. For this example, f of x is x to the 1/3 minus x to the minus 2/3. Let's take the derivative. F prime at x is 1/3 x to the minus 2/3. We just subtract 1 from 1/3. And then we have a minus 2/3 times x to the minus 2/3 minus 1. So that's a minus 5/3. Now let's go ahead and let's simplify this. I'm going to write our negative exponents in the denominator. So our first function is 1 over 3x to the 2/3. And then we have a plus 2 all divided by 3x to the 5/3. That just helps us to get a common denominator without having to deal with negative fractions. We can then see that our common denominator should be 3x to the 5/3. I'm going to make a note here that x to the 5/3 is x to the 1 times x to the 2/3. So we know when we get a common denominator that we're going to have to multiply this number by x because it already has an x to the 2/3. So this gives us an x plus 2. Now to find the critical number, we're going to take our derivative and we're going to set it equal to 0. So we're going to take the numerator and set it equal to 0. So we have x plus 2 is equal to 0, and this gives us x is equal to minus 2. So x is equal to minus 2 is a critical number. Now we're going to see where our derivative, f prime of x, is undefined. That is going to happen where our denominator is equal to 0. So we're going to set 3x to the 5/3 equal to 0, and that gives us x is equal to 0. Now, here's where the most common mistake can happen. We cannot assume that x is equal to 0 is a critical number without going back to our original function right up here and checking if it is defined at x is equal to 0. So we can check f of 0. This is 0 to the 1/3 minus 0 to the minus 2/3. This term is just 1 over 0 to the 2/3, and that is undefined. So that means that x is equal to 0 is not a critical number. Now let's look at our graph. When x is 2, it's a little hard to see because it's so small. We have a horizontal tangent, and the slope of our function is 0. And there is actually a local max at that point. And then you can see from our function that at x is equal to 0, our function is undefined and we don't have a critical number. Our last example is f of theta is equal to 4 theta minus tangent theta. I had to include one of these examples because when I've taught this in class, I found that the trig examples are the most challenging for students. We're going to start by taking the derivative. So we have f prime of theta is equal to the derivative of 4 theta, which is just 4. And then we subtract the derivative of tangent, and that derivative is secant squared theta. Now, I don't know about you, but I don't really have the secant values memorized. So let's see if we can change this derivative to be in terms of cosine instead of secant. So let's set secant squared to be 1 all over cosine squared theta. Now we can go ahead and get a common denominator, cosine squared theta. Now we're going to have to multiply our 4 by cosine squared theta, and then we subtract 1. Now we can find where our derivative is equal to 0. We're going to take the numerator, set it equal to 0. So we have 4 cosine squared theta minus 1 is equal to 0. This gives us cosine squared theta is equal to 1/4. So cosine theta is equal to plus or minus 1/2. Now we have to find where cosine theta is going to be plus or minus 1/2. Since it's a plus or minus, this value is going to happen in all 4 quadrants. So we're going to have theta is equal to pi over 3, because cosine pi over 3 is 1/2. And now to account for all the other values that are not between 0 and 2 pi, we have to say plus 2n pi, where n is equal to 0, plus or minus 1, etc. And then we have theta is, in the second quadrant, 2 pi over 3, plus 2n pi. In our third quadrant, we have 4 pi over 3 plus 2n pi. And then I'm going to have to put it over here. In our fourth quadrant, we are going to have 5 pi over 3 plus 2n pi. I have a lot of videos on trigonometry if you need to review any of that. Let's go ahead now and highlight our critical numbers. It's this one, this one, this one, and this one. Now we have to think about where f prime of theta is undefined. If we look back up at our derivative, f prime is going to be undefined where the denominator is equal to 0. But before we go ahead and compute all those points, let's go back up and let's look at our original function. Tangent theta is sine theta divided by cosine theta. So at points where our derivative is undefined, our function is also going to be undefined because it also has a cosine theta in the denominator. Because of this, we are not going to have any critical points from where the derivative is undefined. So these critical points that I highlighted in green are our only critical points. I went ahead and graphed this, even though the graph is really kind of hard to look at. It has all these lines because of the values that are to the right and the left, but what I want us to focus on is these points right here. These points that I'm going to highlight, those are our critical points, and you can see that they are local max and mins. And as we continue to go to the right and to the left, there are going to be an infinite number of those critical points and an infinite number of local max and mins.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.